In the homework, I did not ask for the equations video, but I was really pleased to see people were including them sometimes, clearly to keep them straight in their heads. So the equations, V equals IR, V equals I over C, and C equals IR, and then what are they? Voltage, current, resistance, conductance. Voltage being separation of charge, current being movement of charge, which could be ions as well as electrons. Resistance and conductance, the opposite of each other or the inverse of each other, how easily current moves, and so resistance makes it harder to move, conductance makes it easier to move. And so here's one with high resistance and low conductance. It's a really narrow opening, and so it's harder for lots of electrons to move next to each other through it, whereas here is lower resistance, it's higher diameter for an axon or a wire, allows more electrons to move through side by side, or sodiums to move through side by side, so that's higher conductance. And another person who showed the same things with a little more detail. Both of them are just fine. Question A asked for a membrane with two voltage-gated sodium channels at a little ways apart. Membrane potential is minus 70. Does that mean the charges are acting on each channel identically? And several nice answers. Here's one showing the average is minus 70, but here's one that happens to be a little more positive, a little more negative, and maybe this one is because it's near a secondary active transporter, and so it's getting a little bit more positive charge. Here's another one showing the same thing, but without showing a cause, where this one is a little bit more negative, this one is a little bit more positive, and a little bit more negative. The average is minus 70. And another one showing a secondary active transporter, and so a little bit more positive charge here than by the other one. For B, in a membrane at minus 45 millivolts, is it possible that two voltage-gated sodium channels have exactly the same charge nearby, three charges, in the same relative locations, but the differences in collisions from water molecules opens one but not the other? So it's important to understand that charges are what determine the threshold, but which channel opens is a mix of how close particular charges are plus random molecular motion. It's like a door or a lock that's stuck or a window that's stuck and you jiggle it to open it. That jiggling is random molecular motion hitting the different parts of that protein in many, many different locations all at the same time, but with slightly different averages. It's the source of Brownian motion, random molecular collisions. And so here we've got water molecules that happen to be hitting the top of this and holding it closed in the schematic, and this one doesn't have those collisions, and so the same charge opens the channel. So you wouldn't be able to predict every time you get to minus 45, is it going to be this one that opens or this one that opens? It's going to depend on the combination of charge and these random events, the collisions. A membrane showing channels and showing why there's an undershoot at the end of an action potential. And of course it's because you have leak channels allowing potassium out, but you have a second way, actually many more channels, voltage-gated channels that allow potassium out, and so you get more negative. You're allowing more positive charge out. This one is a little tougher. It's a voltage-gated sodium channel showing when it's inactive, the voltage gate closed, inactivation gate open, when open, and D and E. And then E asked, show in the sketch what might be causing it. So this one nicely shows at minus 70, the activation gate is closed, and for part E, the negative charge inside this minus 70 is pulling that positive charge in. Then when it opens here at minus 45, this one is showing the positive charge is repelling. It is true that positive charges repel, but we're still minus 45. And so it's not logical to say at minus 45 that's going to be repelling. Now this is not something I told you before, but I do want you thinking about it. And that means there must be something going on. If we're still negative, it can't be that positive charge in here is repelling this. What must be happening is that this thing is spring-loaded in some way. That voltage gate is spring-loaded. So this thing is always trying to open. But at minus 70, the spring isn't strong enough to open it, and so it stays closed. But when you get to minus 45, now that negative charge is not strong enough to hold that closed against a spring that's trying to open it. And so at minus 45 it opens. So it's not enough to say that repels. In fact, it must be that we've removed enough negative charge so that the spring can open it. Oh, and sorry, at plus 30, this repels. So this part, I didn't see any accurate answer. I only graded about 8 to 10 of them, but I didn't see any that captured correctly what's going on. And I have to admit, it's because I haven't talked with you about it, but I wanted you to realize there are going to be some times when you see inconsistencies. And if you're at minus 45, that's not going to repel a positive charge. That's going to attract a positive charge. Finally, in F, 3 sketches, same patch of membrane, about 4 or 5 gated sodium channels. During an action potential, they are all open. And here is the first half, showing them all open. And then second half, all closed. Then the absolute refractory period, we're seeing all of them closed. That's certainly with the inactivation gate. Activation gate is open. And that certainly would be the absolute refractory period. Then relative refractory period, you might have some of them are reset, but not enough to get you an action potential. And then toward the end of the relative refractory period, you would have a few still inactivated, but some activated and ready to go, some reset and ready to go, closed and ready to go.